we will start it. Okay, welcome everyone. Today is the second day of the mathematical tutorial. Jakub will go first and today talk about the physics that led to the development of quantum theory. And after his presentation, I will continue with going a little bit deeper into the math and talk about classical and quantum probability, quantum logics and quantum computing and entanglement, quantum entanglement. So.
Perfect. Thank you very much. Could you please also give me rights to share the screen?
Sorry. Of course.
Okay, perfect. Thank you very much. And hello, everyone. Welcome to this afternoon.
It should work, Jakub. I saw you started screen sharing, so it's just a matter of time, I guess.
Okay. Yes, sorry. The technique is taking time to load the presentation. Okay. Here we go. Okay, can you see now? Okay, sorry for the troubles. Okay, so hello everyone. I would like to spend the first part of this tutorial talking about some experiments that led to the, as Michael said, the development of quantum theory. And just to motivate what we will do, we will look most precisely on the question of light, whether it's a wave or particle, which quantum theory has really interesting answer to. And I'm quite positive that everyone here knows the answer. It's dominating the literature on quantum social science or quantum theory. You may know it as wave-particle dualism. You may you may heard some echoes of it in the talk of Katrin of thingness versus anti-thingness today, and so on. But nevertheless, I think it's quite worthwhile to review some of these experiments and to actually think them through what they actually mean and how they contribute to understanding of quantum theory. Actually, Katrin in her talk gives some hints why we should do this. She talks about that physics is mainly practices and forms, which talks about the results of the experiments. She talked about anti-thingness, which I think it's really grasped by this discussion. What is the light, whether it's a particle or rather a wave? And she actually mentioned that the thought from the previous year that everyone should think about double slit experiment, which is one of the experiments we would review today. So even though you may have heard of these experiments, I think it's worthwhile to go through them and to try to better grasp them. And what I will try to do, especially in the last one, when we were discussing Mach-Zehnder interferometer, I will try to use some of the mathematical concepts or language that we learned yesterday from Michael's part of the tutorial. So even though you may be familiar with the experiments, please try to, I think it's a collective effort to learn something from them once again and trying to apply some of the concepts that we have developed so far. So I will start with the central question. Light, is it wave or particle? Hopefully the presentation will work. I would just say at the beginning that it's a long-standing question, which is not new for the 20th century, but there has been some suggestions, including figures like Newton or Huygens. And as you if you study the history of understanding of light, you would see that there are actually two models that dominated the debate. One was Newton corpuscular model of light, which presumed that light is some particles that spread along the straight lines, and they allow us to explain the phenomena like how optics works, classical optics works, or how, for example, the original photography worked, basically propagating the particles of light from their source along the straight line to some target. On the other way, there are other ideas how we can think of light, and as a comparison to Newton particle model of light, I introduced Huygens wave model of light, which either think of the light as wave, which is propagating not from one source, but basically every single point in the space which is reached by that light will become a kind of source of this light again, and therefore the light has, for example, the ability to bend behind some obstacle, which, yeah, there are numerous phenomena that you may know from your everyday life. For example, this light, which this like straight line, which would be explained by the Newton understanding of light, but there is also this bending, this like light that we can see all around these slightly open doors, which seems to be impossible to explain without the wave model of the light. Michael, if you want, please interrupt me anytime. Okay, this is somehow dated history. So Newton model would be from the 17th century, Huygens from 19. But in the 20th century, there was two famous experiments that developed this question further. And one is famous Young double slit experiment, which works like this. So imagine that here on the left, on the side, you have a source of the monochromatic light, which means light of one specific frequency of or like wavelength. So for example, red light. And then you have some barrier with two narrow slits there. And then you observe the effect which will be visible on the screen. Here you can see directly the results of the experiment. What you will see, it's something what's known interference effect, and it can be characterized as the basically blocks of like light and dark regions on the screen, alternating from the center to the theoretically to the infinity, to the left and right. First, this experiment for long has been thought as being a proof of the wave character of light. It's simply because these interference patterns, these like changes between dark and bright regions, are easy to explain with the wave theory of light. So, and the idea is that this pattern is a result from the difference between two paths light takes from the two slits. So if I look closer to the situation, narrow these close to these slits, so we can see the slits here. And in theory, if we accept the wave theory of light, then these two slits will become the sources of the light. And if we analyze, for example, this bright region on the screen, we would see that the light going there from the slits to the screen propagates along trajectories which are of different length, and what's matter is their difference. So if it happens like here on the picture that both of these lengths come so-called in phase, that means that the wave, the crest of the wave is of one wave is the same as the crest of the other wave. That means that they positively interfere, and that means that they create a bright spot on the screen. On the other hand, if the distance, the difference in the distance between upper and lower slit is half of the wavelength. That means that they come out of the phase. And that means that they effectively eliminate each other when they arrive to the slit. So yeah, you can calculate it quite easily. So you will expect bright spots to emerge on your screen in places where d is the distance between the two slits. Sine A and this theta is the angle which goes from the slits, from the center of the experiment to the place you are interested in. And so this theta would characterize the bright spots on the screen. On the other hand, so they are this is a real number, and they are all the the difference has to be proportional. Sorry, not real. The whole number of the wavelengths, and the dark spots. This formula remains the same, but the difference has to be half of the difference has to be half of the wavelength. So it seems that this experiment really suggested that light is a wave, that there is not much empirical evidence that you may provide to think about light in terms of particles. But there comes another famous experiment of the 20th century, which is photoelectric effect experiment, which is the experiment that Albert Einstein got the Nobel Prize for. It's actually not theory of relativity, but explaining this experiment. So what happens here in this experiment? So what we have here, we have evacuated the tube, which means that it's a tube without any particles. And we have photoactive metal here, which means that if a light is coming to this metal, the light has the ability to kick out some electrons from the material. And if we apply some electric current to this circle, then the electrons will be traveling to the other electrode. And in theory, if they reach the electrode, they will produce a current that goes through the electric circuit. What Einstein was starting with when he tried to understand this model, he started with this wave model, which assumed that light is actually this wave, which could be characterized by two variables. One of them is the wavelength, which is lambda here, and second one is the amplitude. So the lambda is the difference between the heights, and the amplitude is the size of the individual waves. And what is important and what we will need to understand this experiment is the concept of intensity. The intensity is proportional to the square of the amplitude. So if you have, for example, water waves, so if you double the amplitude of the wave, you will actually have energy transmitted or intensity transmitted, which would be 4 times the original. So there is a square proportion between those two. That's important. And the frequency is just another variable which we can devise from the wavelengths, because it's speed of the wave divided by the wavelength. So they two are in a direct relationship with the use of the constant, which is speed of light. So we have these two, and if we follow the wave model, you will expect something like this. So there are 3 predictions that comes from the wave model. First one is that if you can manipulate the light here, so the characteristics of the light coming here. From the wave model, you will expect that light with higher intensity, that means bigger amplitudes, will eject electrons with greater kinetic energy. So we have bigger waves, they come to the material, then kick it out with greater energy. So they have better energy, and they more likely can reach this other electrode and create this current. Second one is that light with higher frequencies, that means that the waves are more often kicking to this metal, will result greater current, because every wave has some likelihood to emit those electrons, and therefore if we increase the frequency, we will increase the number of the electrons kicked out from the material. And the last one is that there is light of any intensity and frequency will be able to eject electrons. So even though we may have light of really small intensity and small frequency or low frequency, over the time you will basically vibrate the material, and at the end you will eject some electrons, no matter how low is the intensity or frequency of your light. But if you do the experiment, it's not ideal if you have 3 predictions and none of them is correct. It is exactly what happened with photoelectric effect, because if you do the experiment, we did it in the laboratory in my physics classes. If you increase the intensity of the light, you will get greater currents, not greater kinetic energy, but more electrons coming out of it. If you increase the frequency, you will actually increase the kinetic energy of the electrons. And the last one, there seems to be certain threshold below which if you have lower frequency, you are not able to eject any photoelectrons. So it seems that none of the 3 predictions are really explaining anything about what's going on with respect to how light is likely to transmit the energy to the electrons. So what they had to do, and what Einstein had to do, was to replace this wave model with something else, and this something else is once again partially particle model of light, but I would call it quantum model of light, which seems to somehow connect both of these aspects. So we will be thinking, or Einstein introduced actually photons, which is the concept for particles of light. So some bunches of energy that produce this effect. And usually we visualize them like this, because those photons are characterized by their frequency. So it seems that some waviness is still playing a role in their behavior. So what Einstein came up with, light consists of photons. One photon always interacts with one electron, so no wave interacting with number of electrons, but 1 to 1. Each photon in this theory carries energy proportional to its frequency. So if I increase the frequency, that means that I increase the energy of individual photons. And it leads to the fact that if the energy of the photon is higher than some minimum, it's called work function of the metal, the photon transfers its energy to the electron, which is ejected from the material, and the remaining energy is transformed into kinetic energy. So actually, if I apply the light of low intensity, the individual electrons do not have enough energy to emit the electrons from the material. And yeah, so if we follow the logic of Einstein, and as I said, he got Nobel Prize for that, so it's probably not stupid, we would probably conclude that light is rather a stream of particles, photons more specifically, which does not really solve our wave particle problem. Yeah, so it seems that both of these models say something about the nature of the light. And fortunately, and then I will proceed to the second experiment I would like to present here, is the famous double-slit experiment, which is used to clarify the ideas of quantum theory, which somehow combine the properties of, I would say, particleness and waviness of the previous experiments. Maybe the language is failing me here, but I will try to clarify. So if you are not familiar with double slit experiment, I will introduce it. I will follow the drawings are from famous Feynman lectures on physics, volume 3 on quantum mechanics, when he used this experiment to explain a lot about quantum theory. So once again, we have double slit experiments. So we have some source of something. Then we have wall with two slits, which are not far, really far enough. It could be nanometers, for example. And we have a backstop or the screen, and we have some detector to detect what is actually happening there. And I will try to present the experiment in three settings: one with classical particles, then with waves, and then with the particles of the microworld. That means electrons or photons or whatever. So imagine in the classical version of the experiment, we have simply this machine gun which is shooting bullets. So we have really a strong wall here and backstop of sands and a sack of sands and so on. And we will try to predict, so the gun is not precise enough, it's going to all directions, but we try to understand what will be the probability that the bullet from the gun will reach the backstop of in the specific place characterized by this X in the backstop. We can understand the experiment quite nicely when we alternate when we open only one of those slits first. So if we open only slit number 1 and then we open slit number 2, you would expect the intensity of the bullets to be found in the backstop, something like this. So the highest probability, the highest intensity of the results is it's on the line between the gun and the first slit. It's the maximum, and it goes to minimum to both sides. The same applies to slit 2. And if we let both slits open, which is crucial for the experiment, then we will see that those two will just add up to each other. So instead of 2 bumps, they will add to each other, and we will have 1 bump, and where the probability, the highest probability will be just behind the center of the experiment. Yeah, because those both are really high here. So nothing surprising. So the most bullets will be found near the center, and it will go to 0 if the bullets rockets to different directions. Okay, now imagine the same experiment with waves. So now we do not have machine gun, but some device that goes up and down regularly, and it creates and it propagates through the medium. You can imagine, for example, the surface of the water there. So you try to create the waves. We need the walls to actually absorb the waves, so they do not complicate the picture, they do not come back. But so we have waves only coming from the source, going through the slits and to the detector or absorber. And as the wave model of the light suggests, then each of the slits will become a source of the waves. And so now in the space between the wall and the absorber, we will see nice overlaps of those two waves coming from each of the slits. So it's very much the Young experiment that I introduced before. So what you would expect here. But first of all, let's talk about this intensity. As I said, with the waves, what we have to do is we take the height of the waves and take a square of it, because the energy of the waves is the square of the amplitude of the waves. So if we close the slit number 2 and let only number 1 open, the intensity that we will find will be the same as for the classical particles. So the maximum just across to the first slit. If we close the slit number 1 and open the second one, we will see the similar or mirror image of the first one. But if we combine them, we will get what Young got from the experiment, which is this interference pattern. So I already explained that, but what happens here is that we have two waves coming here, and because the waves follow trajectories of different paths, they will either interfere positively or negatively, and the places when it interfere positively, the intensity will be the highest. But right next to it, we will have this dark region, or region where the water will not transmit any energy from the waving, and so on and so on. What is interesting mathematically, we do not sum the square of those amplitudes here, but we first, what we do here, we sum the amplitudes and then look for the square of the sum. So we first found how high is the wave that will arrive there, and we use the square to find the intensity of this wave. Okay. And now what happens if we do it with the particles? Because we are interested in the question of light. And if we think of photons as microparticles, then it should clarify something about the nature of the microparticles. In this specific instance, we do not have photons, but we have electrons. So we have, it's called electronic gun, which is a really nice word, but it's basically some wire which you will heat up and it will emit electrons, and you will use electric field to accelerate the electrons towards the backstop once again. So basically you have the same situation as with the normal gun, machine gun, and with the bullets, but we are just shooting electrons now. Okay, what happens if we have one or the second slit open alternately? We will get the same picture as in both of the previous cases. Not surprise, it's the same. So no matter what those microparticles really are, they should. What the probability is, I will explain this notation later on. But if we do, if we open both slits, what we will get is this unmistakable characteristical pattern of interference. So it means that with the microparticles, in this instance of the experiment, it seems they behave like waves. There is something wave-like going on with respect to these microparticles. But how you can, so if you thinking of microparticles, then the question is how they express something like wave behavior. Yes, Michael?
So yeah, just a little detail to your nomenclature. Microparticles is you just mean very small, like, because I guess there's a way to get this. Are you literally meaning micrometers, or is it more nanoparticles?
Yeah. That's correct. Yeah, it's it would be. This characterization would apply to all particles, basically, because no matter what is the scale here, all particles feature this behavior. But in this experiment, we are talking about nanoparticles. So we are talking about electrons, or probably some nuclei, or photons, and so on. Yeah, but the only difference is that we need to create this double slit small enough to allow. So we may think of sending cars here, but then the wall and the slits would looks quite differently from what we present here. But that's a good question. So I mean with microparticles, I think of like microwort versus macrowort. Okay, so if we are seeing some features of wave-like behavior when we are sending the particles. We may do two things, and they actually did it, and we have quite interesting results. First of them, we can limit the intensity of the rate in which the electrons are actually emitted. So one way you may think of it, that if you have lots of electrons, one of the ideas would be that one goes to the slit number 1, second goes to slit number 2, and they will interfere somehow later on. But you can limit the intensity or the rate in which you emit the electrons, and you can have actually only one electron in your device all the time. So whatever happens, the electron has to be responsible for all of this. If you do this, and they actually did it, you will start seeing these like white dots on the screen, emerging on the screen. These dots, yeah, they are one hit of the electron on the screen in the experiment. If you have only few electrons, you probably don't understand anything what's going on. But if you keep the experiments going to the B letter, C letter, and D, you will see that even though you allow only one electron to enter the device at a time, the result is the interference pattern. So it seems that, yeah, there is some waviness you would have to attach to individual electron. Otherwise, you would have quite hard time to explain this interference, which is appearing on the screen. In other words, that's for me something what was really like mind-blowing when I was learning about this experiment, that there are regions on the screen where the electrons are simply not allowed to hit. There is something preventing them from hitting this region of the space or this region of the space, even though they are able to bend further from the center. So that's something going on, interesting. Okay, so that was, so it seems that the electron is somehow, yeah, using both slits or to propagate through the experiment. So the last thing that we may use, and this is something what Chris talked about yesterday, is to try to get more insights on what's going on. And in the experiments, you would use it by introducing the source of light, which you would place behind the wall with two slits. And the basically just flashes of light that allow you to see where the electron is actually going, whether it's through the slit 1 or slit 2. Yeah, so you try to distinguish what the electron is doing in our experiment. So if you do this, so we introduce this light source, as once again, the idea to introduce this source is, this light source is to be able to recognize which slit has been used by the electron to go through the device. If you do so, you will find, and you will use only one slit, then you will find this pattern on your screen, similarly to the second slit. But, and that's quite interesting results of this experiment, if you let both open, and if you have information about which slit has been used by the electron, the interference effect is no longer there, and the pattern that you will see on the screen will be just the sum of the two, like it was the case for the classical particles, like the bullets. So that's something, yeah, as Katrin suggests, we should all meditate about double slit experiment every day. So if you can follow it, then you basically, I would say, understand everything about quantum theory. But it seems that something is going on, that there we have a part something, which is, for example, photon of light, and it exhibits the features of the wave if we are not looking, but it seems that it behaves much more like the classical particle if we are able to distinguish, in this case, two options how the electron could reach the wall in our experiment, which is, yeah, what to take of it. I think it's one of the key points of the quantum theory, how to make sense of this result. Okay, and so this observation led to, I would say, to the development of quantum theory as the mathematical theory, as the model, how to interpret this. And they are actually, at least Feynman present it in the way that you can clarify these results with three principles, that you can make sense of it with the use of three principles. So I will introduce these three in the way he used them into lectures. The first one, I will not elaborate on what an ideal experiment is, but the principle goes on. In an ideal experiment, the probability P of an event is equal to the absolute square of the complex number phi, which is called the probability amplitude. And this is something what's known as Born's rules. And it allows us to think, if we are talking about probabilities of something happening, this first principle says that we should think first about probability amplitude, and we will get probability out of it only if we take a norm square of this amplitude. The second principle, if an event occurs in several ways which are indistinguishable, the probability amplitudes is the sum of amplitudes for each of them. So in our experiment, the interference effects occurs. So we are talking about two possibilities how the electron can reach the wall. One of them would be characterized by this phi 1 and second one with this phi 2. And it says that the second principle says that if those two ways are indistinguishable, we cannot make the observation and be clear what happened. Then the amplitude is the sum of those amplitudes, and then we may take a probability by taking a norm square of this amplitude. And the last one, if the experiment allows to distinguish between alternatives, then the probability of the event is the sum of contribution of probabilities for each of them. In this case, interference effect is not present. So if we are able to distinguish these two parts, obviously we can generalize it into n paths. But if we can distinguish them, those alternatives, then we first take a norm square of the amplitude, and then we add them together. So in this case, the probability is just the sum of probability along these two paths. I will just go back to I will try to clarify it with the, once again, with the pictures from the microparticles or nanoparticles experiment and other nanoparticle experiment observations. So here we have two paths, how the particle can reach, or the object can reach the backstop. These two are indistinguishable. That means that we take their amplitudes, probability amplitudes, we sum them, and then we take the square norm square, sorry. But if we are able to distinguish, that means that we first take a norm square. We have the probability P1, which is here, P2, which is probability here, and then probability P12 is just the sum of the two. Okay, any comments or questions with respect to this? My plan for the rest of this 1 hour talk is to use these principles to explain, and something what we learned yesterday, to explain something about another experiment, which is Mach-Zehnder interferometer. But I just want to make sure that we are on board here with these three principles, this experiment. Yeah, Michael?
Will be a tricky question because I don't know the answer to it. But, is there any intuition why it should be square of amplitude?
No, it's an interesting question. I may think of several answers, but the most intuitive from what I was saying is this. I think it's the empirical observation that the energy transmitted by waves is the square of their amplitude. So if we are actually, it's something what we knew by observing the nature, and I would say, at least to me, it's intuitive, because if we are talking about wave behavior of those microparticles, it's not a right word for them any longer. But if we are talking about the wave propagating through some medium and interfering with each other, and if we are talking about, yeah, then the probability, probably the question is whether energy is good analogy to probability here. Yeah.
Another thing which comes to mind, I mean, I think there's a formal theorem that these things only work with exponent 2, like it's a formal argument, like I forgot the name, but another thing maybe why, like just to give intuition why there might be two things multiplied together. It's like you were saying, it's like multiple ways to go there, and it's as if one has to look at a sender and a receiver. So in a sense, if I often have this in quantum mechanics, the way to understand it is to read it as there's something, a bra and a cat, and it has to match. So it's as if you send out and probe a system, and then you look at the echo, and then you look at the probability, and it always, but okay, it's just hand wave.
Yeah, but it's a good question. I will look into it. Okay, but at least my understanding of these, I really like what Catherine was saying today, because basically these principles has not been derived theoretically, but this has been derived to explain the empirical and experimental results in the laboratory. So yeah, I don't know whether I'm interested in finding why in this respect. For me, this is, and we are looking for the mathematical model describe the reality that we somehow share with other species or something. But that's my personal note on that. Okay, so if there are no questions, I will go to Mach-Zehnder interferometer, which in a sense is quite analogous to double slit experiment, but it will introduce another way how to look into it, and I will try to show you that the principles that we derived with the use of double slit experiment and the formalism that we used yesterday is useful to understand the results of this experiment with the interferometer. So how does it look like? I first have the schematics here, and then I will give you a picture how it looks like in the lab. But you basically have a source of light here, S. Then you have this beam splitter, which is half mirror, or how is it called in English? Basically, mirror that allows half of the light to go through and half is reflected to the orthogonal direction. Yeah, so yeah, it's beam splitter. So it split the beam into halves in this case, and so you have light which is transmitted through it, and you have light which is reflected. And you have two regular mirrors here, which just like change the direction of the light to the second beam splitter. And in this second beam splitter, somehow the two light beams combine back. So we have this guy going from the up to the beam splitter, part of it reflecting, from part of it going down. Here is a possibility that the light goes through and also is reflected. And what we have in the last part of the experiment, we have two light detectors. It can be screens, it can be cameras, whatever. And also we have detector 1 and detector 2. And the question is to the audience, if you don't know the experiment, where would you say the light goes in this experiment? We have two detectors, one source of light, and it goes through the mechanism. What I should stress, what is important, is that the path along the upper branch of the experiment and the path along the lower branch of the experiment is the same. That's important for the result. Any ideas?
So I'm sorry, but I have another additional question. What is a beam splitter? If you could explain, because without this knowledge, I cannot even try to answer the question.
That's a fair point. So the beam splitter, we have a source of light, we have a beam of light going here, and the splitter split it into halves. So half of the light will go through, and second half of the light will reflect to the lower branch. And now we have two regular mirrors. That means that all of the light will reflect, and here we have the second beam splitter. Yeah, so half goes through, half will be reflected.
Okay.
It's just a guess, you know. You have to go to laboratory to see it. But
I think that to both of them, D1 and D2.
Okay, yeah, that would be, I would say, quite intuitive if you see it for the first time. Yeah, so half goes here, here, half goes straight, and half goes here. That means, yeah, we should reflect something in both. If you do the experiment and you do not disturb it, if you do not do anything extra with it, you will just use this interferometer, all the light will come to detector 1, which is parallel to the source, which means that none goes to D2. And if we actually observe the experiment, so if we, for example, have a detector here which will click, if you have the idea that yeah, if you are talking about photons, if you have idea that the photon goes over here, then if we observe the path, then half of the light will go to the D1 and the second half to D2. So that means that what the Martian intuition here was the classical one, the observed one, where the probabilities adds. Yeah, so we will just add the probabilities, what happens on individual beam splitters. But that's, yeah, thanks for the guess, Marcin. Yeah, I would guess the same. It's
so this is because, you know, this is because I'm coming from observational sciences. even if you are talking about physics, you know. So okay.
Yes, Emma, another question.
So is this the classic observer experiment? And my other question with this is, if the undisturbed versus the if observed, obviously you're observing it after the fact. So then there's that time where is that come into play? Because you have to see it, you can't measure it to see it went into D1 unless you did observe it after it already occurred. This is my conundrum a lot of times when I
Yeah, I should probably clarify what I mean by observed. That means if we are able to distinguish, so if you are imagine one electron here or one photon, sorry, here, and if we apply the classical logic either or, so it goes either through or is reflected, then we may try to detect whether the electron is in the upper or lower branch of the experiment, like we try with the double slit experiment with the light source. So trying to distinguish between upper or lower part of the experiment. In practice, how you do this? One of the possibilities is, for example, at least intuitions would be if you attach, for example, some fine spring measuring device to the mirror, and the idea is that if something is going through and reflected on the mirror, you will have a signal. So the question is whether you will get it here or here. And what was the first question, Eva? Whether is observer?
If this is the observer experiment, where if something is observed, then it changes. Is this that experiment?
I'm not familiar what is observer experiment, but there is definitely something what's called observer effect in quantum theory, which says exactly what I distinguish between the principle 2 and 3 in the previous slides. So whether you are able to distinguish or not, that means whether you observe the experiment or whether you measure it somewhere or not.
Okay.
Yeah. Okay, so this is what we will find, and now I will try in 8 minutes try to show you how we can make sense of it with the principles that we derived. Okay, first of all, this is how it looks like. It's really a nice experiment. You can do it with a laser source. Now you have the laser here, you have these two beam splitters, these two mirrors, and you have just screens here. So you either see a green dot here or green dot here, or if you're doing something wrong, you will see no dot, but you are probably not really good in what you are doing. So this is, yeah, it's a simple experiment that you can actually do. I suggest that we will try to use these 3 principles that we derived from the double slit experiment. So the first principle asks us, or says that we should think about probability amplitudes, and then we need to look for the absolute square of them. So first of all, what is the probability amplitude? That the light that goes from the source S will go to the upper part, so it will be transmitted through the first beam splitter. So the first of all, I will just introduce the same notation that Michael did yesterday. So we have the initial state, which is the vector. It's somehow more difficult because it's wave function, actually. So we are not talking about the vector space of finite dimensionality, if I'm not mistaken, but an infinite. But it doesn't really change what we will be doing here. Yeah, so we have the state vector, and we use this Euler formula here that Michael introduced. So we are talking about waves, but we can represent it with this exponent. It's the standard way how to think of waves, but it's not that important. I just introduced it that we have some object to think about. Then what we know from the fact that we use beam splitter, which split the light to both paths equally, that means that the probability of transmission is 1/2. And so if we introduce, for example, 2 photon, well, it's a bad example, but if we introduce beam of light here, it's actually half will go through and half will be reflected, which is given by these probabilities of transmission. And just what I used here, so this is the Dirac notation that Michael introduced yesterday. So we have the original state of the system, so this light going from the source, and we are asking how likely is it that it will ends up in the upper branch. So you look for this product state, and we can get the square of it. And we know that this is 1/2 because we have this perfect beam splitter. And the same for reflection. Then the interesting question, the first principle says that we should look for this probability amplitudes, which we should square. So the question is, what is actually inside these brackets, what we should square? And sorry, I will just take a water. There are actually 4 ways how to solve this equation, but I will use only 2 of them. One idea is that if we have this original state where it's a wave function, and if we think of the wave that is just transmitted, we would probably think of the wave which is not changed by this transmission, and there is this normalization parameter which allows us to get the probability P of the transmission 1/2 as we observed in the experiment. So what I did here, it can be derived, but I will not go there in this lecture. But the idea is that we will think of the transmitted state as not changed, so it's the same wave, but the amplitude of this wave is changed by this factor 1 over the square of 2. If we do this product, and if we square it, we will get the probability of 1/2, which is exactly what we needed. I will just get the other one, and then I will give space for the question because that's important. But there is another normalization factor that we can use for the reflected state. And if you ask what we can square to get 1/2, there is another probability, which is I over square root of 2. Yeah, so if we look for the length of this complex number, we will multiply with this complex conjugate. Sorry. Conjugate. And sorry?
Conjugate.
Conjugate. I cannot pronounce it. I can pronounce it in Czech, but not in English. Conjugate. Okay, so we will get I square, which is -1, but because we have absolute value here, we have 1. Sorry. Okay, so that suggests, yeah, and I will try to explain why we have used I in one of the slides if I have time here. But it's to give you one intuition. Michael yesterday talked about Y as being orthogonal to the classical numbers. So the imaginary part of the light is in some sense orthogonal to the classical one, and that's, yeah, and if we are talking about the reflected part of the light, it make intuitive sense to use I here instead of here, but it's just an idea. Okay, so if we accept that we have these probability amplitudes, yeah, which is 1 over square root of 2 or I over square root of 2, we may think of with the use of the, yeah, sorry, one more step. We just look at what will happen on the first beam splitter. So we have the original one, and the probability amplitude that it will go to transmitted state is 1 over the square root of 2. And here is the formula for the reflected light. But because we need to get to the detectors, we need to get through the second beam splitter. Yeah, so now we will try to look not for the product state of the original one and transmit it, this one, but for example here, which stands for the light being transmitted and reflected on the second one. Yeah, so I will talk about this direction. So the light goes through the first one and will reflect on the second one. So this is this TR aspect, which goes to D1. And yeah, we can use this chain rule. So the idea is that if in the probability amplitude in the first one is 1 over the square root of 2, and the probability amplitude of the reflection, which is the second one, is I over the square root of 2, we can multiply them and get the probability amplitude of the whole path, which is I over 2. Yeah, okay. And if we do this for this, all the rest, we will just combine those two numbers in various ways. So if we are talking about TR, which is transmission and reflection, it will be multiplication of these two. If we talk about reflection first and then transmission, it will be multiplication of these two, but in the opposite order. Then for transmission and transmission, we will just multiply twice this. So we will have 1/2. And for the reflection and reflection, which is most interesting, so we have I over square root of 2 multiplied by I over square root of 2, which is I square, which is -1 over 2. So this is the amplitude for this path, which goes reflection and another reflection into detector 2. And now, yes, Michael?
Just a quick question. Can you show the path for transmission and transmission? Don't see it.
Transmission, it's this one.
Yes, number one. And then?
And the second one is on the second beam splitter.
Oh, okay. So you leave out the reflection in the...
I simplify the picture by not thinking about them. Yeah, but that's a good point. I should include, or I should at least note that I do that. Okay, so I'm talking about what happens on the splitters. Okay, so I will be quickly to just use the other two principles. So the first principle says that if we cannot distinguish between the two paths, meaning upper or lower, the probability amplitude is the sum of amplitudes for each of them. Yeah, so for example, if I go back, I can use this path, transmission and reflection and transmission to get to the detector one. So according to this second principle, I will first sum the amplitudes and then do the norm square of them, which is simple algebra. So we have I/2 plus I/2, which is 1. Yeah, so we edit the amplitudes, individual amplitudes of the two possible paths, and the probability is 1. What is interesting, what's happened if we discuss the other detector? Once again, if we cannot distinguish the paths, we will add sum the amplitudes first, and as there are 1/2 and -1/2, we will get 0 amplitude, and if we square it, we will get 0 light coming to the detector 2. Yeah, and I will just conclude with the principle 3. So the principle 3 says that, so if we introduce some measurement device and we are able to say which path has been taken to reach the detector, we need to not sum the amplitudes, but sum the probabilities. So we will first get to the probabilities, which means that we will square each probability amplitude first, and then we add them together. Which, if we have I/2 squared and I/2 squared, we have 1/3 and 1/4, sorry, which is 1/2 if we sum them. And sorry, this is wrong. There should be separate squares here, but I believe, yeah, sorry, this explanation is wrong. We should first have a square of the individual amplitudes and then sum them. That's a mistake on the slide, but the next row is right. The next line is right. So if we have 1/2 squared and -1/2 squared, we will get the same result, which means that if we do not, if we observe, we prevent those two cancel each other before we square them. So that's what's mathematically what's happening. And I have two options now. I will probably
We lost you, Jakub. Oops, probably you can't hear. Well, I guess he will have to reconnect again. Okay, he's reconnecting. Is everything clear so far? Is it difficult to follow? Is it too much elaboration, or is it just the right amount?
So I'm fine with this. So
Okay, very good. Yeah.
as for now.
Yeah. Yeah, I'm good too.
Hello, everyone. I'm back. Sorry.
You
I'm
switched into
sitting
the
next to my
alternate.
modem and it's working, but
You switched into the parallel world for a second.
yeah. I don't know where I ended for you.
Well, you just interfered with yourself negatively. So
Okay.
you were just explaining the sum, like when it's observed. When both are observed, why it adds up.
Okay. So if it's fine with you, I will try to finish it in 1 minute.
Okay. Are you still here, Jakub? The universe really wants us to have a break, I guess.
So this is the part related to non-observation.
Yes.
Quantum.
It shows maybe the importance of the intention. I could really need a break, but well, but make sure also, if you're interested in this, to be there on Friday. It will be on quantum games. It's really nice. Okay, Jakub is here.
Okay, I will not try to reshare my screen because it seems that that's what's collapsing my connection.
Fine.
I will just conclude with 2 notes, if I may.
Can I ask a question?
Yeah.
I mean, I get that this was for the quantum particles, so it like the phase all the phase differences are important for interference effects, so for them to cancel out. So this only works when you don't see them. Then the phase can add up or subtract. If you always watch, the phase is forgotten and it just adds up. So I wonder if you do the same thing with lights, then it should be either through both, or it should be different, right? When you do it with light beams, or not?
Well, what experiment you mean? Or
Is this for quantum particles, or is this for light? What you just explained.
The last one is with light. Yeah.
Okay, and how does then I don't understand. I mean, because light can be observed or not. It doesn't. I mean, when you do experiments with light, it's not like a quantum. It's not like you don't have the quantum observer effect. Like, so, or am I missing something?
Yeah. That's. What I wanted to present to you is this quantum lab, which is the virtual lab where you can, for example, do the interference experiment with whatever object you like. And the idea with light would be if you use like single photons for that you would need interference of those single photons with each other.
Then you use a quantum property of the light, but because otherwise you cannot. Maybe it works with optics, but I wonder how could you implement with just classical optics, like wave optics? How can you implement an observer effect, like watching or not watching? I don't see how. Okay.
I would say okay. I probably do not have good answer to that. I was thinking about it. When I was thinking about the experiment, I was thinking about like individual photons. So then you need the superposition of the particle being in both branches, and the observation force it. Yeah, the language is failing me here, but to decide whether it's there or not, if we are talking about the superposition of being there or not. Yeah, but how this relates to, I would have to think about it, and I will try to give you some answer in the next tutorial.
Okay.
I just wanted to conclude that in the slides I will send Kelly to upload to the website of the bootcamp. There is a link to this virtual lab where you can play with the components of these experiments. So you can build your own interference experiment, and it's a really challenging game. So there are actually like some puzzles that you have to solve with the use of interference effects. So it's quite a nice way to spend some time and to get more familiar with the quantum theory if you do not go to like a real lab. So the experiments will be there.
Yeah.
Okay, so that's all from my side. If there are any questions, I'm happy to address them. Otherwise, I would not like to steal you from the break. So we can break here and come back in 17 minutes for Michael's part of the tutorial.
Well, any questions?
No, just thanks, Jakub, for sharing that. So yeah, no questions yet.
It's a pleasure, Matt. Okay, so thank you all, and be back in for Michael part in a while. If you want to stay, Matt, and chat, I'm happy.
I will go and take a drink.
Yes, we probably should honor that.
Okay.
On a completely different note, did you ever? Oh,
is it okay if it's recorded, Matt?
Oh, it's fine.
Okay.
Yeah, I was wondering, did you ever come across a conclusion to the paper presented last year at the IQSA 22? Like you had presented some joint work between you and someone from Australia.
Katarina, yeah.
Yes.
We are still working on it. It's still work in progress, but
okay.
we will have a draft for the conference in September.
Oh, fun.
But we proceeded quite well, I would say. But because of some other job-related issue of Katarina and mine, we have not finished it yet, but we will present a draft in September and at ASA. And yeah, I'm happy to share it once it.
Oh, that'd be great. I'm very interested. I've been busy myself, so kind of took a detour in a different area of research lately, but I'm still really interested in coming back to it.
I've presented the ideas at quantum information processing in Vexia in June, but it was without the paper, only some like ideas from it. But yeah, so once I have the paper, I will send it to you.
Okay.
But we have to finish it this year. So
okay. Oh, good. So
okay.
Yeah, maybe. Do you have a homepage on your Charles University website? Do you have a faculty homepage?
Yes, but that's not much information there.
Oh, okay.
I can give you the link, but there are only like courses we teach and the published articles. But that's all.
Yeah. Okay. Fun.
Okay. So see you in a minute.
Okay.
Perfect.
Thanks.
Okay, good. Okay, welcome back. So now comes the second part of Tuesday afternoon's tutorial. And can you see my screen?
Yes.
Okay. Is it? Oh, it's not full screen, right? So let's go switch into full screen mode. View, enter full screen. Is it better? Should be better like this. Okay.
Yeah, that's full.
Okay, so this is the list of topics. We'll talk about Schrödinger's cat, classical versus quantum probability, superpositions, qubits, linear operators, unitary operators, quantum gates, and entanglement. So you see, this is an introductory lecture. Well, no, I mean, it's kind of daunting, and I mean, we will just build the intuition for this, so that next time you hear these concepts, you will have an idea that it's not as scary as it sounds like. Okay, quantum superpositions, and the famous example is Schrödinger's cat, and we all know that there's something very strange about Schrödinger's cat. So it doesn't really behave like a real cat. It's something mysterious. So, and in language, there's no way to understand it. And we will see that when you try to do it with mathematics, you see that there's a difference in the way to explain what does it mean that a cat is at the same time alive and dead, like Schrödinger's cat supposedly is. Okay, so in order to build up to this point, we start in the classical world, and we start with classical probability. So imagine you have this jar, and it has 50% of its marbles are red and the other blue. So we say the classical probability, if you randomly pick a marble, it's 50% for each color. So note here that what is implied is that even if I don't look, or even before choosing, whatever marble I choose already had a specific color. It's just here probability, and it's just expression of my ignorance. But if I would, in principle, know everything, then there would be 100%. There would be no randomness because I would know. So here, it's just reflecting my ignorance. This is a classical picture. So what would be the quantum equivalent? And I believe that everyone who's joining today was there yesterday too. So we know that yesterday we discussed how to represent events using vectors. And we can try to do this here. So instead of talking about red and blue points here, we will now start to think to translate this into a vector model. So in order, we know that a marble is, when we look at it, when we measure it, is either blue or red. It's not both at the same time. So therefore, we will represent these two categories by orthogonal categories. And we will represent them by by these two axes, the red axis and the blue axis. And so how do you represent a red marble? We want to represent it by a state. You remember that a state is a vector in a Hilbert space, which has a length 1. So that's the only ingredient we need. It has to be normalized such that it has length 1. And this doesn't define its direction. So we have a certain freedom to assign what we mean by the red marble, and actually it doesn't matter. So the entire axis actually confined to length 1 is a equivalent representation of the red marble. And same with the blue marble. Both representations represent a blue state. Okay? It's just this axis which counts. Oops. Yeah. And now, how to represent the jar with the red and blue marbles? So, what would you do?
You would you'd have 1 over root 2 red plus 1 over root 2 blue.
Yeah, this is already the quantum idea. So, and I mean, it's good, but and in a sense, I wanted to provoke exactly this. Thanks for answering. The classical jar is represented by the 2 vectors here, which are not added yet, because it's either or. When we start adding exclusive categories, we do stuff which in the classical world is impossible. So in a sense, this mixture here in the jar cannot be represented by a vector. It's both, you have both arrows. So it's not a quantum state. It's a mixture. We call it classical mixture. And there's a way to also represent this mathematically. This would lead to so-called density matrices. It's also not very complicated. In a sense, it's just the expression of what I tried to draw here. Just 2 arrows. Okay. And if, say, the distribution would be different, then the one arrow would be more weighted, would have more statistical weight than the other. Here it's 50-50. Okay. This is a classical state. So now what you meant is, yeah, so I repeat this, these 2 vectors is not a vector, is a configuration of 2 vectors. Now, what you meant is what happens if we superpose this trait? Because if we have these 2 vectors and we are in a vector space, well, okay, we can add them. And as you also mentioned, I think, is to renormalize them, right? So adding them is not yet a quantum state because it has lengths larger than 1. And in order to bring this, to shorten this so that it lands on the unit circle, we just need to renormalize it. So then it's a proper quantum state. So we are talking about this. So now let's look at this the property of this state. So let's now we can do a measurement, a quantum measurement, and ask for the probability. What's the likelihood that we measure blue? What's the likelihood of measuring red? And okay, mathematically speaking, this object here is a linear superposition of the blue and red state, and in the quantum framework, we often talk about quantum superposition. It's just a linear superposition of vectors. Nothing spooky about it. So now we remember if the probability of measuring blue would be obtained by Born's rule and the projection. We would need to take the projection down. This has length square root of 2, which is 0.7 something, and then you have to square it, gives 1/2. And the same with the probability of finding red. So in a sense, this quantum superposition has exactly the same statistics as a jar, as the marbles in the jar. So, and before I told you, yeah, but it's something else. So something we need to understand here. And once we understand this, we will understand Schrödinger's cat. Is it clear? So what I propose here is to define a quantum marble and which is just the superposition of these two, and to assign them just for illustration quantum purpleness. Okay, these are like strange marbles, and we call them P. And okay, it's just in mathematical form. And now it's just again reformulation in the graphical form. The blue marbles, the red marbles, and then the purple marbles. And now what's quantum about these? Because I told you these are strange marbles. Well, before answering this question, let's do the same. Instead of adding them, we can subtract them. And these are like quantum yellow marbles. Again, what's quantum about those? So let's just understand the property. So let's take one of these purple quantum marbles and we ask a question. So this is, are you blue or are you red? Okay, if we ask this question, it's like a quantum measurement. So then we will get the answer, either red or blue. That's what it will collapse. This is what happens in quantum mechanics. And so let's say, yeah, it was 50%, it will collapse to red, and with 50% to blue. So now say we just asked, say we measured blue, and now we repeat this measurement. Then within 100% of the cases, it will again say blue, and the same with the red. So there's a certain, this is like this principle, like repeated measurements, if they are immediately or repeated, also in quantum theory, will give the same result. This is a type of persistence or consistency. Now, yeah, repeated measurements produce consistent outcomes. Now let's ask, are you purple or yellow? Okay, so what will happen? What do you think? We take this quantum marble and ask it, are you purple or yellow? Any ideas? Otherwise, I call you. Eva, what do you think?
Perhaps 1/4. We would have to change the formula, so it's a 25% chance.
Okay, let's see. I mean, we have this purple here, yeah, this purple marble, and now we ask on the slide before. I asked, are you red or blue? Okay, so there we know we would have to project it on these states. Okay, and then to calculate the probability for the outcomes. Here now, I don't ask, are you red or blue, but I ask this purple, are you purple or are you yellow? Okay. So, and then the outcome can only be purple because this purple state has 0 projection on yellow, has 0 probability. Okay. Is this clear?
It's just like playing quantum tic-tac-toe.
Exactly, and this is, I mean, it's kind of, you have to do it a couple of times to get a feel, and this is why the quantum tic-tac-toe is so great, so simple, but I mean, not so. But and here too, it looked like so simple, but if I just would present it, everyone would you would not build up the intuition. No. And then say, okay, here the outcome is purple. We ask it again, are you purple? And so on, yeah, ad infinitum. Okay. What about the other way? What is the other way? We start now with the red. And now we ask the red, are you purple or yellow? What do you think?
It should still be 0 though, right?
Why? Why?
Well, because do we know that it's red to start? So it can't be purple or yellow. I know that probably I'm incorrect, but it's okay. I'm going to go with it.
No, you are not incorrect. You are correct and incorrect. You are correct in this way that I didn't specify what type of red marble am I talking about. Am I talking about a classical marble, like my first picture suggested? Then you are correct. Or am I talking about the quantum red marble? Okay. So let's first assume that this is a classical marble. So it has a red color. Regardless of how often I ask it, it has a red color. This is the type of objects we are used to. Yeah. So if red denotes a classical, like if this object denotes a classical object, state, I mean, state is a bit misleading because then we are thinking about quantum state. So if this denotes a classical object, then it's 0%, as you said. But if this denotes a quantum state, well,
5%?
Yeah, then it's 50%, right? Because then, like, you have a 50% chance to project it on purple, and I told you yellow doesn't matter whether it's pointing down or up. You will have it's just this axis which counts. It's all yellow, so you will also have a 50% on the yellow state. Okay, if you understood this, you already understood a lot. And then you ask again, and then you have consistency kicking in. Okay. Voila. And also, you know, now pretty good. Okay, if I ask a question.
Okay, so I have a quick question on this. So because we're measuring a second time, it's shifted from the first measurement. Once we've measured it, it drops into a classical state. Is that why
No,
it's 100% after?
no, I mean, it drops into a quantum state, which is well defined. So before it was in the superposition, we always need to talk about relative to what, to a given frame of reference, and the frame of reference is always defined by what we measure. So here, if I ask, if I measure now the quantum red regarding to the purple and yellow frame, so this is orthogonal. If I obtain purple, then the red becomes purple, so it collapses, and it becomes the purple state. This is I didn't plot this here, but it's like an update. The state has lost its redness and now is purple. So it's the measurement in quantum mechanics produces reality in a sense, produces identity. And then when now I ask this purple state, are you purple or yellow? Then we are back in the where you answered first. Then it has to be purple because it has zero projection into yellow once it's purple. But all these states now are quantum states.
Okay, so but once we have the measurement, we know what it is, but it still remains quantum. Just to.
It still remains quantum, exactly. Yeah.
Okay. Thank you.
And ultimately, the entire world is quantum, but it appears quite classical. But this has other reasons. So. Okay, qubits, I guess you have heard about this concept, and basically it's not different from what we have here. We can call, instead of talking about colored states, we just assign them 0 or spin up, just different ways. You can call the red 1 or spin down, and then the purple, well, they would just be linear combinations. So it's just different expression of the same thing. In quantum computing, you typically see this, and like in entanglement experiments or so, you typically see this. So next time you see this, you're not afraid. You know how to translate it to our quantum marbles. Okay, and the other thing which in quantum computing comes up, and Jakub will talk about it on Friday in quantum game, in a quantum game setting, and also we will have a talk on Thursday about linguistics and quantum computing. So once you have qubits, you can transform them, and the transformation happens via gates, and gates in quantum computing, they perform logical operations. So I wanted to show how this works. There you have a blue marble, a 0 qubit. You send it through a gate. The gate will do something to this vector. It will not change its length, but it may rotate it or flip it. This is what the gate is doing. For example, say this gate will take your 0 state and it will transform it into this superposition state. While a 1 state will be transformed to the yellow quantum marble. There's a matrix representation of this. No need to be, if you don't understand this, is fine. But just if you think of this in 2-dimensional vectors, what is happening, you know that this is a linear transformation, and in linear algebra you can represent them by matrices. This is just the matrix representation of the Hadamard gate. If we represent the 0 state by the 1, 0 vector, so it's pointing in the x direction, and the 1 state with the 0, 1 direction. And yeah, these are linear operators, and they map vectors to vectors or states to states if they don't change the length. Not every linear operator respects the length, but in quantum mechanics, the like so-called unitary transformations, they respect the length. Yeah, so the Hadamard gate is a unitary operator. It preserves the length and the angle. So if you have 2 vectors, 2 states, you send them through Hadamard, they will be mapped to 2 other states. So say you have red and blue, they will be mapped to purple and yellow, and they were orthogonal before, they are orthogonal after. So this is not every linear transformation has this property, but unitary transformations have the property, they respect the length and the angle. And okay, this is not important, but I mentioned it nevertheless. So what this is doing, it's mirroring at this axis. So the blue becomes this and the red becomes this. So you see we have the Hadamard gate is a type of mirroring operation. And as with every mirror, if we mirror twice, if we reflect twice, again we end up with what we started. So and it's its own inverse. So application of this operator twice is represented by multiplication of operators, gives the one which is the identity. It's not the 1 state, it just means nothing happens. Okay, we can check this. We have the Hadamard gate in matrix form, multiply it. we use the rule of matrix multiplication, and it gives an identity matrix. No problem if this is too much. It's just expressing what is happening here in pictures. As I mentioned, unitary operators map quantum states to quantum states. And this is, we just talked about the Hadamard gate. And if you open a book on quantum computing, you will see other gates too. And they just change other things. They add a phase, multiply the state by a phase, they rotate and flip. Yeah, so it's, you got the idea already with the Hadamard gate. But all these gates, when this ensemble of gate, when you combine them, you can build a quantum computer. Okay, now let's go back to Schrödinger's cat. So now we can map to, like, represent by a quantum state what happens. So we have the cat, which is dead and alive. And now, how would we represent Schrödinger's cat? Any ideas? Who hasn't talked yet?
Purple.
Right. So this, right? Yeah. But what about the yellow? This one. Well, which one is Schrödinger's cat? So I leave it as a homework. Usually people tend to have this in mind, but this would also be a Schrödinger's cat. When you ask it, are you dead or alive? Again, 50%. So is not clear. But you see all these, it's so much more helpful, or it makes it clear if you know how to talk about things, strange things like Schrödinger's cat, if you have this mental image of vector spaces in mind. And this is why I think social scientists who want to explore these quantum ideas, it would be very helpful for them to learn this type of math, because even if they never use it, it will make them more fluent in expressing their ideas. So it's not clear. We have two types of Schrödinger's cat, I guess. It's also not so important. So the next, before I go on to the next topic, entanglement, I wanted to ask any questions about the superpositions and Schrödinger's cat and quantum gates.
So I've got a question, but I've got a question concerning the previous slide. I mean the slide where the gates are. Yeah, okay, and the operators. Was it used to change the angle? This gate? I mean, when you were rotating, rotating the vectors before, then as I understand, so such a gate was used, like this Hadamard, right?
Yeah.
Okay.
And the other ones, as you can see, they don't really change. So they flip here, but these two flip the axis, but they don't rotate. It's just a flipping.
Oh yeah. Okay, yeah.
And then these they multiply. They do something with the phase. Of course, now when we have complex numbers, you can play around with the phase. You can multiply this. Yeah.
Okay.
Question.
Thank you.
Okay. So I assume no other question. Then let's go to the second part, entanglement. So entanglement is often described by looking at the two quantum particles. They are called Alice and Bob. Can be either typically spin systems, and you can Alice be represented by spin up and Bob by spin down, or the other way around. So in quantum computing would be it would mean you are operating on two qubits at the same time. Okay, and these qubits are entangled, and now we want to understand what does it mean to be entangled. So in the short form, entanglement is a quantum version of correlation. It's not totally exact, but I won't explain this too much. It's like correlation works with classical objects, right? And in order to see whether the properties of two classical objects are correlated, you have to see them. So they need to be locally in proximity so that you can access their state at the same time and compare it. In the quantum world, they can be separated by the diameter of the universe, and they can still be entangled. So in principle, you may never be able to compare, but they will still change in unison or affect their state in unison. So there's a subtle difference between entanglement and correlation. Just mentioning it here. Okay. So let's find a way to represent this in the picture. So let's look at stress versus happiness for typical human. Typically, the more stressed you are, the more sad you are. When you are relaxed, you are happy. So there's like a anti-correlation on the stress happiness axis. So there's negatively correlated. This is how we would say in statistics. And now, okay, you could make a linear regression and you would extract correlation coefficients also. So now, instead of looking at typical humans, let's look at Bob, and Bob is a quantum particle. So Bob is a qubit, so has not access to any continuum of emotions or of mental states. It can be like Bob is either chill or stressed. And so represented as a quantum state. If he's both, so if he is in this superposition, then it can be either or with a 50% chance. So, and it's like an ambiguous state. And Alice, the same, either happy or sad. And again, let's assume that she is in a quantum, like a superposition state. So now let's have both of them meet in their quantum superpositionness. And so how would their state be described? What possibilities if we measure them? Well, there would be four possibilities. Either like happy, chill, happy, stressed, and stressed, sad. So you have all these four combinations as possible outcomes of their combined state. And all of these have 25% probability. So the quantum state representation goes like this, and this is similar to the quantum tic-tac-toe representation. So we just take the state of Bob, multiply it by the state of Alice. Now you have these two spin states, so you just concatenate them. The factor of 1 over square root of 2, they combine. So you reach 1/2 here. And this can be rewritten as this. This is the way you typically write multi-spin states, where the first always refers to Bob's state and the second entry to Alice's state. So, and you see, we have 4 possible outcomes. So, and they are equally weighted. So there will be the same probability for either this, or this. If we measure them. Before we measure them, they are in the superposition state. This is the way you would represent quantum mechanically this statistical distribution. Now, this is called a product state, because this is exactly how we arrived at the state. We just took the product of the first wave function with the second wave function. And it's like in classical probability theory, if one attribute is distributed according to statistical distribution P1, and the other according to distribution P2, and the combination of it, if these two attributes are uncorrelated, is just P1 times P2. This would be uncorrelated. So in the same, whenever it's a product state, they are not entangled. In classical probability terminology, Alice and Bob are statistically independent, uncorrelated. Okay. So let's just play around with the state to get a bit feel for it. So we have this two-person quantum state, and now we measure it. Okay, so we measure, but we only measure Bob's mental state. So, and we measure it. It turns out Bob turns out to be chill. Okay, so what happens after measurement? What happens to this state? You know, it will collapse, and it will collapse to something which could be chill. So it has but we only assessed, so this means that all these contributions, which with the first spin is red, they drop out, they're projected out. So we will end up with this state. And this can be rewritten as the product of Bob state times the superposition state of Alice. So Alice is still described by the quantum superposition she had before. So nothing, the measuring Bob didn't affect Alice, okay? Because they were not entangled. It's as if they can go on in their life without really interacting. Therefore, if now I measure Alice, is she sad or happy, I find either or with probability 1/2. And vice versa. So if I had, if Bob turns out to be stressed again. Okay, now let's have them after a while. Then they start to interact, and let's assume that now the state space has shrunk to these possible outcomes. So either whenever Alice is happy, Bob is relaxed, and whenever Bob is stressed, Alice is sad. Something like this. So what happens now? And this would be referred to the situation where the state is and their state is entangled. Why? Well, first, this would be the representation as a wave function. And now we have to show that this cannot be written as a product state. Actually, I will not show it, but you can show that it's not possible. This is an example of an entangled state. And whenever you cannot write or decompose a quantum state as a product, by definition, is entangled. So now when I assess a state with a probability 1/2, it's either this outcome or this outcome. And also we can say that assessing Bob's state determines Alice, even if they are far apart, and vice versa. This cannot be used to communicate. It's just whenever you assess, you measure, say, Bob state, and you find blue, you know immediately that Alice state is yellow, but according to the Copenhagen interpretation, by doing this, Alice state is affected by measuring Bob because its ambiguity is lifted. So this is the difference between correlation and entanglement. It's very subtle. Yeah, so this would be the spooky action because there's a quantum collapse involved. According to the Copenhagen interpretation. According to other interpretations, this is just a pseudo problem. So, yeah, I think we talked about this, that the entangled state is the analogon of statistical dependence or correlation. And I mentioned that entanglement is a little bit, there's a different, subtle difference between entanglement and correlation. And that's it. So I think we are good in time this time. Are there any questions? Was this sufficiently clear?
So maybe I have a question, but at this time also concerning the last slide. I'm sorry, but okay. So is it possible to say that this entangled state is the same as a perfect correlation? Because so here is the statistically dependent correlated. Okay, so we know what does it mean. But the perfect in a perfect correlation, one measure at one so one measure determines.
Yeah, this is different. It's difficult again. Because you could have perfect correlation in a classical system, and there's a way to have also. You could also represent here. It is a linear superposition of these two. And they are perfectly correlated, that's true, but there's also, when you think back of the marble example, you could still represent them by a classical mixture of either both up or either both down. Yes. But then I told you this is not a linear superposition. This would be a classical classical mixture, would still be perfect correlation. And in both cases, would it be a perfect correlation? But
okay, so yeah, so it is, as I understand, is it enough to have an information about one of this entangled state?
Yes,
yes,
yes. But in the classical mixture, just by measuring one, the other one would be determined, and you just happen to pick up this marble, which
that's right.
And whereas in the quantum thing, the measurement itself will break it up, and then it's perfectly correlated. But the measurement would first break the superposition; it would collapse. Whereas when you start with the mixture state, there's no collapse anymore. The measurement doesn't collapse anything. So this is a subtle difference. This is like, before you look, it is a combined object. And in the mixture state, it's always been separated, two separated objects.
Yeah, okay.
Yeah. It's subtle, but okay, Eva.
Okay, so I'm sitting here. Whoops. Oh, I'm sitting here, and I've literally in the past 2 months I've read like 1,000 papers on quantum theory and social sciences, and mostly in cognitive science. So I am looking at, let's see, at Mintzpacher's paper from 2001 with weak quantum theory, and it looks closer to standard probability because they're using P's. And I can't put my hands on the other ones. Ertz was another one, but it looks like a standard probability that they're using instead of the vector signs or vector formulas. Is there another, and they're specifically saying it's quantum probability that they're using. But I can't put my hand on paper to actually give you an example. But is there another way to do this, or am I perhaps misunderstanding something?
I mean, the other way to do it, which works just with probabilities, would be the cubism. I mean, this would be just a reformulation of quantum mechanics, where you wouldn't talk about amplitudes, but you would just talk about probabilities, but it comes at a cost of having this weird pi matrix Chris talked about. And I don't think that Atmansbacher would talk about this. I think he would always look at squared. He would use the apparatus of standard quantum mechanics, Copenhagen, but then only look at probabilities and look for interference effects or so. I have never really read Howell's paper, so if you can send me the reference, I can help you further. Yeah.
I have a stack of paper, so I'll look over the next so and send it to you, and then it'll be a better question.
Okay.
I'm just trying to kind of formulate how to put my dissertation together. So if I need to go toward vectors, then I kind of just need to change things a little bit. Thank you so much.
Yeah, you're welcome. Yeah, maybe if you send me, I can answer, probably not before the workshop is over, but over the weekend.
Okay, thank you.
Yeah, you're welcome. Other questions?
I just wanted to add 2 things that may be relevant to what Eva and Marcin said. With respect to Marcin, it's probably good to point out that what Michael presented is maximally entangled state, and it's only one extreme that you may get. So entanglement is not either or, but it's a property of the state. So you may have like only partially entangled state. So, and I read recently a nice book from Leonard Susskind, Understanding Introduction to Quantum Theory. It's a really good introductory book. So if you are interested to learn something about quantum theory, and if I'm not misinterpreting the book, they said that what is so interesting about entangled state, or for example this maximally entangled state, is that you have full information regarding the whole. So you always know that they will end up being together, but you have, until the measurement, you have no information about individual parts. So that's something interesting going on, because you have full information that you can get physically on the whole, but not on individual parts, which is not what you have in the classical state. And with respect to Eva, I think I'm not familiar which paper you are talking about, but there is in quantum theory, there are so-called weak measurements. And there is the question is, if I said, for example, when I was talking about the principles, whether the situation was observed or not, or distinguishable paths or not, then the interesting question is how strong the measurement has to be to actually collapse it. And there is a bunch of literature on on how to make measurement weak. It does not limit like conceptually quantum theory, but in many applications it's actually possible how to get partial information about the system. But we go into much details to this intro, but I guess that Harald may talk about that.
Sorry, it was a 2001 paper, the first one that I recall, the one that used Ertz used fruits and vegetables, but it was 2001 or 2002, and they were using animals and vocalizations of the animals. And when they just tested the animals, everything correlated fine. And when they just tested the vocalizations, everything was fine. It was one of the initial social science, cognitive science, quantum papers. But when they actually asked people to put things together like horse neigh, and then tiger neigh, or cat meow, tiger meow, then they started entangling things. And it was funny, but they tested against, they did like broad searches through like Google Web search on like what were the possibilities of these occurring. So they had like a massive amount of statistics to work with, and then they pared them all down. So that's the paper I'm trying to put my hands on, because that was kind of like a foundational paper. And it looks like a lot of other people built. And I don't think it was Busmeyer or Bruza that wrote that one, but I have to double check.
Perhaps Sozo?
Good possibility of that.
Yeah.
I have so many stored, and I have stacks. I actually have like a whole
yeah, there's a whole school from Ertz, Dirk Ertz. So if you Google Dirk Ertz, he's in, where is he, Jakub?
No, I have him. He was a 2010